Okay, welcome to the second video of 1.3 quantities of atoms. Now in this video we will be covering a bit of the first one and the third item that's seen there, as well as some examples that's for calculation using the relationship n equals to m over m, so lowercase m over capital M, and also its arrangements. Slide in the lecture note that you should be looking at is this one. This is slide 6. All right, let's start. Okay, so you can see the relationship there that is used to calculate the number of moles in a sample or material in moles. So n, now if you can add information to those three things there, n equals to, also n means number of moles, and the unit is in mol, mole. I usually use square brackets. That's a pretty common thing to do for units. And next one is m. Lowercase m is mass over sample of a substance, and the unit is in grams. Again, square bracket g. Finally, mm, capital M or capital double M. I use capital double M because m over m doesn't really, let you easily remember things. So I tend to use double M. Double M means molar mass. It's got two m's anyway, so molar mass. Unit for molar mass is grams per mole. So g dot mole and superscript -1 or g slash mol. Either is fine. Now, how we can use that? Here's an example. Now, these two examples can be found on page 24 of the Essentials workbook as well. But yeah, gives you a chance. I'll give you a chance to write them down. So in the first example, it says determine the number of moles of zinc if 4.25 gram was present. Now I've done the workings here. Now if you're trying to find the number of moles, focus on the number of moles, which is n. In this formula, n can be found if you knew the mass and divide that by molar mass of the substance. N is unknown, that's in moles. M is given in the question, 4.25, it's in grams. Molar mass is 65.38 grams per mole. Now this number could be just straight off find from the periodic table. So I have a periodic table handy. You can find it in the Essentials as well. So this is for zinc element. If you put these two numbers into this formula, so 4.25 divided by 65.38, you can find the number of moles to be 0.0650 moles. Now we'll talk about what's called significant figures later on, but you'd notice that I added 0 after 6.5. Now it's going to be important later on in chemistry life. In question, 4.25 was given in 3 significant figures. It wasn't 4.250. It wasn't 4.3, even if you round it up. This was given is 4.25. It's considered to be 3 significant figures. Whereas next value that you can find from the periodic table was 65.38. That's considered to be 4 significant figures. In chemistry, we picked the smallest significant figures from the question and use that to answer. Okay? So if this was 3 significant figures, your answer will be 3 significant figures as well, because that's the lowest. Moving on to the second example. So second example was to determine the mass of sodium hydroxide in 5.60 moles of the material. Okay, so sodium hydroxide is what you're working with. Sodium, Na, hydroxide, OH. So NaOH is its formula. Okay, right. So we are now trying to find mass. So we need to look at this m here, the lowercase m. If you can rearrange the formula, it should become something like this. So m equals to n, number of moles, times by molar mass. So it's just a simple rearrangement here. If you can't do it, do ask me later on. Now, here is the known information. N is given as 5.60. 3 significant figures here, and that's in moles. M in grams is something that you are trying to find out. I should have written that down too. MM is 39.998. How did I find out? By adding molar mass of Na, 1 oxygen and 1 hydrogen. Okay, hydrogen being 1.008 and oxygen being 16.00 and sodium being 22.89 or something like that. If you add them up, add those numbers up straight off from the periodic table, you should be able to get 39.998. And if you do the calculation first, so m equals to 5.60 times by 39.998. You should be able to get 2 to 4 point something something on your calculator. Again, lowest significant figures that was given in the question was 5.60. 5.60. That's 3 significant figures. So I answered it in 3 significant figures as well. I rounded up or down all the decimal points. Okay. Right. Last couple of slides here. Oops. How about that? Now, when you think of moles and number of particles that's involved, I hope you're thinking about this number, 6.02 times by 10 to the power of 23. This number is known as Avogadro's number, and that's the guy, Avogadro, and his number. Please do take it, please do know it. Symbol used for that is actually Na, capital N and capital A subscripted. This constant value can be used to find the number of particles, which is just capital N, number of particles. Yeah, in the material using N equals to N times by lowercase n times by Na. So number of particles present equals to number of moles times by Avogadro's number. Okay. For example, determine the number of water molecules in 5 moles of water. All right. So N, which is the number of water molecules, okay, equals to 5 times by 6.02 times by 10 to the power 23. The answer, N, should equal to 3.01, 3 significant figures, times by 10 to the power of 24 molecules. The unit here is a counter. When you count, say, cookies, you will count it as 1, 2, 3. There is no other counter. We are counting molecules here, so you can just say molecules or just a number. You don't have to have the unit there. All right, I believe that's it. Apart from the equations that are, this is just a summary. So 2 equations that I just introduced. So N equals to M over MM, and N equals to N, number of mole, times by Avogadro's number. And if you want to know how they can be rearranged, these are the rearranged version as well. And we'll do the questions from 16 to 20 in Essentials workbook. And that is it. So make sure you write down these formula and a rearranged version of it, and make sure you practice using them in class. All right, I'll see you then.